The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Thank you very much, Eric. And while we were having a struggle with the four-letter codes, I offered to make a bunch of them up for Eric, and he suggested, no, maybe you should just stick with the talk on limestone. So we'll stick with the talk on limestone. We'll also talk a little bit about ground lightweight aggregate and talk about some of the benefits of this. And as we start to go through this, I'd be really remiss if I didn't talk about the people doing the heavy lifting on the project. And it's really Hanoi and Teng Fei who've done a lot of the developments, and then two undergraduates who are working on this, Selena and Mitchell, who are really doing a lot of great work on here. And one of the things I wanted to start off and I want to talk about is I want to talk a little bit about the idea of how we're measuring the reactivity of various binders. And one approach, and this approach is used a lot because it's a very good approach, it's a very easy approach to use, but it's using isothermal calorimetry. The idea here is that we're going to measure the heat that's released during hydration. We have a rule of thumb with Portland cement that the heat that's released through the exothermic reaction is going to be related with the hydration of cement. However, I think just looking at heat alone may be really an oversimplification of this problem, and I think many times we're going to draw incorrect or incomplete conclusions just by looking at the heat from isothermal calorimetry. So the next 20 minutes or 18 minutes or 17 minutes, I'm going to talk a little bit about how we might be drawing some of the wrong conclusions if we're just focusing on isothermal calorimetry. Now, this is a plot that comes from Igor de la Varga, and he's in the room hiding out behind a beard back in this area here. But this was some work that he did where we were looking at high volume fly ashes, where we were using a lot of fly ash to replace cement. And if you looked at these, you would say, well, here's the heat released per gram of cement, so this whole difference here must be the reaction of the fly ash itself. And that's essentially the pozzolanic reaction that's kicking in there, and it's this huge amount. But if we took a step further, what he was able to do is he was really able to say that there's a lot more to this and a lot more of what's going on. So we have different reactions going on and different forms of heat that are being released, but we also have particles doing different things. So some particles are reacting, some particles are providing a place or a surface for reactions to occur in the nuclei. Some things are going into solution, and sometimes the dilution effect just gives everything else a little bit more room to stretch out and do its thing and to react. So really the whole idea is we're looking at systems with a bunch of different things going on when we just start replacing some of the powder. So here you can see some work that was done, and this was with Igor and Dale Vence, where we used the NIST hardcore soft shell model. And the basic idea here is this is where you have just pure cement. You see all the little red balls representing the different size particles of cement. But when you start replacing 40% of the system with an ash or a filler, you see the same particles appearing in there because we've matched the particle size distribution, but now they're going to react at very different rates, and that's going to have a very different impact on the overall performance. Now if you take the filler out or you take the ash out, now you have the system where effectively what you've got is a system that's completely got a lot more room, and you're going to have differences in reaction. And the whole idea behind this was that we could tailor systems where we could actually start to look at a typical 0.3, which is shown here in blue, that system where we had fly ash, which is shown here as M2 with the dark line, but then two cases where we essentially put in a quartz filler, and then a case where we simply remove the filler, and we're able to see that in each one of those cases we have a different overall heat release. And what we're going to do is we're going to look at this and we're going to say, oh, that's the real data, but then we're going to interpret that data on the next slide here and say, well, all of this difference here is not simply due to the reaction of the fly ash. We have additional things that are going on here. Part of this is the green, which is the effect of the increased spacing. That gets us about a third of that overall heat, is the fact that we've got more room for the particles to be reacting and hydrating in the system. We've got the nucleation effect, which is about a third of the total heat that's released. And then about a third of it is the overall fly ash that's reacting in the system. So while we saw a massive change in the hydration, only a third of that is really due to the reaction of the fly ash itself, where 2/3 of that is coming from other sources inside of the system. So as we start to look at that, the question was, can we start to look at this and interpret this when we start to look at other types of materials and other types of binders that are going on in the system. And the two materials that we're primarily going to be looking at here are limestones, whether we're using a Portland limestone cement or whether we're using the limestone as a filler. All right, and in this particular case, we don't expect a lot of reaction with the calcium hydroxide. We may have some reaction with the aluminates, and more importantly, we may get calcium dissolving into the system and changing the pore solution composition. And then we also wanted to look at ground lightweight aggregates. And one of the reasons we're looking at ground lightweight aggregates is we hear people saying we don't have enough fly ash and we need the effect of that supplemental material. We can't get consistent fly ash, so this is a question of, is there a possible other source out there? So the ground lightweight aggregates are essentially, they're common. The smallest pieces of this, or the powders of this, the dust of this, is something that's readily available. It's an aluminosilicate, and it can be pozzolanic if it's ground to the right size. And this is really what we wanted to start looking at. So again, just a reminder of these two different systems that we'll be looking at. One is the Portland limestone cement system, where we've done a lot of work, where we've got sort of the typical OPC system. Here's the OPC system with about 4% limestone in the ground. The limestone is in yellow. So when you look at this, you're going to look at this and say, 4%. There's a limestone, there's a limestone, there's a limestone. The big thing that you need to notice when you look at this is when we're intergrinding the limestone is it's very, very small. All right, so it's a much smaller particle size, and it also impacts some of the overall size of the cement that's inside of the system. And then when we look at a full blended system over here, we can see both the 15% limestone now shown here in yellow, and then 20% slag shown in this beautiful orange color throughout the overall system. So we'll be talking about the effects of intergrinding, but again, we need to remember that when we start intergrinding materials, we're going to have very different size distributions, and the limestone is going to be typically very, very fine. Again, the ground lightweight aggregate here, it's going to be made from an expanded shale, slate, or clay. The material is heated to bloat it up, so the whole idea of making lightweight aggregates is you try to capture gas inside the material as it heats up, makes the material more lightweight, but then you end up with a lot of fine powder at the end of the day. And what you can't use for aggregates, the question is, can you use this as a ground supplementary cementitious material? So the whole idea here is we're going to look at an average 5 micron particle size and an average 8 micron particle size with two different lightweight aggregate chemistries. So we're going to go through a testing process where we look at all of these different materials here, where we're looking at cement, fly ash, quartz basically being an inert filler, limestone, the ground lightweight aggregates, slag, and we have a lot of additional characterization on where, because of time, I'm not going to get into that. But I want to talk a little bit about one of the plots that we've developed that I think has some interesting components to it. To start off, I wanted to just show you we have measured the total heat release, and this is the same plot that we were showing before. We've got the heat release per gram of cementitious material versus time, and you look at this and you say, they all look the same. They all kind of go high and to the right, like a good picture or something like that. All right, but the basic idea is we're liberating more heat over time, but as I've said, we can't really distinguish what's going on in terms of the hydration of all these materials simply by looking at this graph. We can take the derivative of that and get the rate of heat release, and now all of a sudden we can see sort of the same things that Scott was talking about earlier with accelerations that are happening when we get finer particles, but it really leaves us with an incomplete understanding of what's happening in the system. The other thing that we could do is we could actually start to bring in thermogravimetric analysis, where all of a sudden now we can take these pastes and we can heat the hydrated paste from 100 degrees to 1,000 degrees, and we can essentially measure the mass change and use this to determine the amount of calcium hydroxide that's being consumed. The amount of calcium hydroxide that's being consumed would give us a great indicator of how pozzolanic that particular material is. So when we start to do that, we start getting plots like this, which may cause you to have a headache or may cause you to say, wow, that's even more confusing than I thought it was. But let's just walk through here. We've got the cement here, where as it hydrates, it's generating more calcium hydroxide because we're hydrating more of the system. If we dilute the system, we take 20% of the cement out, we're going to be down here around what we see for the limestone mixture here with it shown in red, where we essentially are producing less calcium hydroxide in the overall mix because we have less cement in the mix because we've replaced cement with something else. The thing that gets really interesting is when you start looking at some of these other graphs down here, where you look at dilution, where you look at the ground lightweight aggregate, and then when you look at the other ground lightweight aggregate here, where you can actually start to see the calcium hydroxide decreasing over time. And what this is saying is the pozzolanic reaction that's occurring is actually more than the continued hydration of the Portland cement. So instead of continuing on this increased trajectory, we now have the effect of dilution, which slides this down, but even further, this gets slid down by the overall pozzolanic reaction. And trying to separate these curves out can become really tricky, especially when you're trying to figure out how pozzolanic a particular source is. And I'll show you an application at the end where not only how pozzolanic is the material, but how much calcium hydroxide it consumes is very, very important when it comes to some durability-related problems. So what I would like to make an argument here is that isothermal calorimetry on its own isn't enough, and there's some alternatives that we can really look at. And one of the things that we've started doing is some testing where we're simply looking at testing calcium hydroxide with a simulated pore solution with these different materials and using this as an indicator of the reactivity of these materials that may be much faster and a much simpler test to go with. So the whole idea here is we're going to take these raw materials that we have, we're going to place them in conjunction with a calcium hydroxide, we're going to alter the pH to simulate what a pore solution chemistry would be, and we're going to use a slightly higher temperature just to try to accelerate the overall reactions. So the whole idea here is we're going to mix the calcium hydroxide, the lime, together with a supplemental cementitious material, and then a 0.5 molar potassium hydroxide solution. We're going to do this at 50 degrees with a relatively high water to solids ratio. And the whole idea here is that what we're trying to do is make sure that there's plenty of calcium hydroxide there to react with the supplemental cementitious material. So when this thing becomes completely exhausted, we've reacted all of the SCM and we have leftover solution and we have leftover calcium hydroxide. So now if we start to do this and we run this through isothermal calorimetry, now we get a very different picture of what's going on. Here we can see what happens when we add slag to the system. Here we can see some of our ground lightweight aggregates. Here we see our fly ash, our quartz, which was surprisingly not exactly zero, but slightly above there. And then we can start to see the limestone, which is this purple fella down here. If we look at the thermogravimetric analysis, again, we see a very different picture starting to emerge where we see a lot of materials that are consuming the calcium hydroxide, our ground lightweight aggregate, our fly ash, and we see the limestone actually giving back some of the calcium hydroxide in the system. And in a real system, this is because it's hydrating more. In this particular case, we think it's because there's a bit of a dissolution going on, and then the material is reforming with some of the pore solution. But one of the things that I found very interesting, and this was really something that Pranoy came up with, and I want to make sure he gets full credit for this, is Pranoy said, if we start plotting these things onto a very simple plot, we can now start to get a much better understanding of what these materials are doing. And I have to say that you'll all probably be much quicker than I was at this. I spent about 30 minutes at a meeting scratching my head trying to say I don't understand how this really simplifies what we're doing, but I think this is an incredibly powerful way to look at the overall data. So essentially, if we plot it with heat released at a particular age versus the amount of calcium hydroxide reduction, as we go further up this graph, we see more typical hydration reactions. All right, we see more heat being liberated. A light's going to be somewhere up here in this 450 to 500 range. B light's going to be somewhere in this range over here. And as we move toward the right-hand side for the audience, we're going to see more pozzolanic reaction taking place in the system. So if we look at the heat that's coming out of each of these tests, we start to see a plot that looks something like this, where we see limestone down here, we see slag up here, all right? We've got our quartz, and then we've got our fly ash, which is this one, and then our 3 lightweight aggregates here. So the very interesting thing is when you start looking at this plot, all of a sudden now you can start looking at these and saying, we can start to classify these different powders based on where they fall on this diagram. Something that's staying here close to zero, it's a very non-reactive material. Non-reactive in terms of pozzolanic reaction or hydraulic reaction on its own. Doesn't mean it's not important in the overall system. Doesn't mean it's not going to change the performance. But the limestone on itself is not what's reacting. We can look over here and we can say slag. We know that that's got some of its own hydraulic capacity to it. Very high heat release versus a relatively low amount of calcium hydroxide change. And then all of a sudden we can see the quartz, right, may have some effect here, but really a lot of calcium hydroxide, low heat. And then all of our pozzolanic materials sort of falling into this nice cluster here, where as we start to change the particle size, we move a little bit over to the right-hand side, likely because we're not at complete 100% reaction. And this is one of the things we're really working on, is to figure out how much of the products are left when we're all done. So if we kind of summarize where we've been up to this point, the approach that we're developing here is really looking at TGA plus internal curing to provide a real strong tool for this analysis. This enables us to really identify materials as inert, hydraulic, or pozzolanic very quickly. The ground lightweight aggregate is incredibly pozzolanic when we start to look at this, and this really leads us into a really great potential application for these pozzolanic types of materials. And one of the things that's taking place is when cements are exposed to calcium or magnesium chloride, there's a potential reaction that can be taking place. All right, so we've got the calcium hydroxide, our CH, we've got our calcium chloride, we've got water. If we react these together, the de-icing salt coming in, we're going to produce this critter called calcium oxychloride. And you may be sitting there saying, exactly, calcium oxychloride, that's what I hoped we would get. Right? This should keep all of us up, scared tonight, all right, cringing, hiding under the bed. This is a nefarious critter. And the reason is it breaks up concrete, especially where you have high salt concentrations. This undergoes a fairly high volume change and can cause pavement joints to start looking at this after only a short period of time. The good news is there's three really simple and easy solutions to this. One is to use topical treatments like sealers. One is to carbonate the surface of your concrete. And the third one is to really start looking at the improved use of pozzolanic materials. So here what we're plotting is the amount of calcium oxychloride that's being produced versus the percent of cement that's being replaced with a pozzolanic material. Now, when we start to use pozzolanic materials here, we would expect everything, if it's completely inert, to fall along this dashed line simply due to dilution. By taking 20% of cement out of the system, we should reduce the calcium oxychloride by 20% because we reduced the calcium hydroxide by 20%. But the big benefits that you get when you start using a pozzolanic material is you start consuming that calcium hydroxide additionally because of the pozzolanic reaction. So in addition to just not having the calcium hydroxide there, we're gobbling up that calcium hydroxide so that it's not free to react with the chlorides when they come into the system. So one of the big questions is the age-old question that you have in limbo of how low can you go or how low do you need to go where this doesn't become a big problem. Right now we're saying around 10 seems to be a good number, what people are seeing in the field where they're not having problems. But this is something that we really need to continue working on to really see where that number needs to be. What we do know now is that the addition of SCMs, fly ash, silica fume, ground lightweight aggregate, anything else that's going to react there to consume the calcium hydroxide is good at minimizing this joint damage. So in conclusion, ground lightweight aggregate has the potential to be used as an SCM. We've talked about a new approach that combines isothermal calorimetry and TGA to quantify the extent of pozzolanic reaction that occurs and to really start distinguishing between materials. And the ground lightweight aggregate, as well as fly ash and several other pozzolans are out there, have a real practical implication to be used in the F3 exposure condition according to ACI. And in fact, we should be promoting the use of these materials when we're using de-icing salts because they're going to improve the overall performance of the concrete. With that, I will either start making up 4-letter codes for Eric, or I will try to answer some questions.
Jason, did you test your raw material, pulverized, the shale, before going through the calcinate or heating process?
We have not tested before going through, but that's something that's on our list of things to take a peek at. Right now we're trying to use kind of an industrial waste, but it would be a great thing to look at.
Any implications of this work for scaling resistance?
Yeah, so the tricky part of this is scaling is going to be much harder not to crack with just this. I personally think that scaling is kind of wrapped up in this, but in addition to this, the scaling issue has a lot to do with placement because a lot of the lighter particles float, and our experience has been it's very difficult to make a concrete with a low slump that scales. It's really easy to make a concrete with a 5-inch slump, 6-inch slump that scales, and it's mainly because we see preferential amounts of fly ash or other pozzolans on the surface. This is something we will be looking at, but there are implications into what's going on in those cases.
Did you have to adjust mixture proportions because the lightweight aggregate absorbs a lot of water?
So in these, what I would say is these are ground lightweights, so they get down to 5 microns. So at 5 microns, they're really almost a completely solid material. They have a very low porosity. We've essentially ground all the holes out of them, all right, if we think about it. That's a great point.
Does it meet ASTM C618?
I have no idea, because I'm not a guy who sells it, but I can look into that if you want.
It does, actually.
Yeah.
The sample that you used was produced by me. And,
There you go.
got all the documentation.
So not only does it meet the standard, but he can sell you buckets of it afterwards. Tractor trailer fulls, all
I
right?
have a 55-gallon drum.
And we'll catch up later on, no.
I think for the last presentation, I'm wondering how we can identify or distinguish the filler effect and the ozonic effect of the fly ash, because calcium hydroxide concentration initially was the same between all of the material, but after a while,
Yeah.
the ozonic reaction takes place.
So the real way we've separated those two out is we've replaced, I feel like the Folgers guy who's replaced the fine coffee we normally serve with something, no. We've replaced the fly ash with an inert filler. In this particular case, it happens to be a quartz powder. The real trick there is you have to try to match the particle size distribution in the surface area, and that is tricky to do. So what you have to sort of mix and match to get something that's really close to try to separate out those two effects.